Hello, thanks for joining us. This is Space Nuts, where we talk astronomy and space science. I'm your host, Andrew Dunkley. Great to have your company again. Coming up in this episode, we will be looking at a really fascinating discovery that dates back something like 10 billion years, and took us a while, didn't it? That is dual quasars that have been found as a result of a galaxy merger. We're also going to look at a bit of a hotspot on Saturn, and it seems it was self-inflicted, but we'll tell you more about that soon. Also, Ken wants to know about the Square Kilometre Array. Bear is asking about infrared light, and Richard is posing a question about the pressure of the oceans underneath the surfaces of ice moons. Really interesting question, that. All coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me to dive into those oceans and many more topics on today's episode is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello. Wow. What's your name again?
Andrew.
No, it's Dave, isn't it? Wasn't it
Dave. I've been called. Yeah, got Dave for a while there. Became a running joke. But
That's right.
we blocked all those people on social media. So that solved it.
So I'll fix that, yeah.
Yes.
But I'm very well, I think you must be that. Very well, and very happy to be here again for another episode of Space Nuts.
Yes, indeed. And it's good to have you here, because if I had to do it by myself, I'd probably just show them the running sheet and say, go and figure it out for yourselves. Yeah. All right. Well, we better get into it straight up, because this first story is rather fascinating, and one that dates back a long time. I looked on the calendar. Dual quasars discovered around 3 billion years after the Big Bang. That's going back a ways, and it's been caused by some kind of galaxy merger. So what was going on way back then, Fred? I know you were there.
Oh, yes. Oh, yes. I remember it well. It's actually, so yeah, 3 billion years after the Big Bang is more than 10 billion years ago. And so that's the real triumph of such observations, that by using some of the world's great telescopes, and they include in this case the Gemini North Telescope, which is on the island of Hawaii. It's an 8-meter class telescope operated by the National Science Foundation, I think, and other organizations in the United States of America. That it means, we've got a really great instance of how powerful these instruments are, because you can see back so far in time. You're looking back 10 billion years in time. In fact, more than that. So what's it all about? Quasars are, I always call them delinquent galaxies, but it's not that good an explanation, because the quasar is the bit in the middle of a teenage galaxy. And it's where a supermassive black hole is voraciously feeding on its surroundings, which is gas, dust, and stars, anything else that might stray into its vicinity. And as a result, they emit copious amounts of energy. And in fact, when I was a young astronomer back in the 1970s, they were thought to be the brightest sources of light in the universe. There are some transient phenomena that actually outshine them now, explosions like colliding neutron stars and things like that, but they nevertheless deliver huge amounts of energy, and it's because of the action of the material swirling around the black hole at their center being excited by friction and electrostatic forces and all the rest of it into a state of frenzy and emit copious quantities of energy, as I just said. So why is this a story? Because quasars are commonplace, and so are double quasars in today's universe. Sorry, not today's universe, but the recent universe. Quasars, we think, are actually extinct.
I was about to ask, because I remember we did talk about that, and yes, what we see is long gone.
That's right.
Well, long gone in our lifetimes, but probably not that long gone in the history of the universe.
That's right. So the nearest quasar, I think, is less than 1 billion light years away.
Okay.
So it's somewhat less than 1 billion years look back time, and that must be one of the last ones before they became extinct. Probably one of the best known is an object called 3C273, which was actually the first quasar to be discovered. 3C is the third Cambridge radio catalogue. It dates back to the 1950s and 60s, I think. Anyway, 3C273, I think, is a bit more than 1 billion light years away. I can't remember the numbers. But that's sort of, where they were the last gasps of quasar activity. But when you look further back in time, you see many, many more. And in particular, if you look back, perhaps 3 or 4 billion years, something like that, you will see quasars that are double. So you've got basically two supermassive black holes near one another, and it tells you that the galaxies that host those black holes have merged or are in a process of merging. You've got to be a bit careful, actually. This is an aside here, Andrew. You've got to be a bit careful with double quasars because I remember this very well from the 1970s. Double quasars were found in that period, which were a bit odd because as they changed their brightness, they did it together or with a slight time delay. And it turns out that those double quasars are actually double images of a single quasar that's been gravitationally lensed by something you can't see in between.
Right.
So that's a different thing, the gravitationally lensed double quasars, bent by the gravity of a massive object intervening in space. Whereas the ones we're talking about now really are double objects, and you can tell that if you look at their spectra. You use a spectrograph to break up the light of a quasar into its rainbow colors and look at the barcode of features that you see in that. And first of all, you can tell by the fact that those features are different in the two quasars that you're talking about two real objects. But then you've got to rule out the idea of a possible accidental line of sight alignment, where you've got two quasars which are close to one another in the sky, but aren't actually close to one another in space. So you've also got to measure their redshifts, which is the way of getting the third dimension. It's how you get the distance to an object. And so there are ones that are known where you've got two different quasars, but they have the same redshift. So the idea of colliding galaxies is what's happening. That's fine. But the reason why this particular story has hit the headlines is that, and it's what you said right at the beginning, this is a pair of quasars in a merging pair of galaxies being observed when the universe was only 3 billion years old. And that's going back much, much further in time than we thought would be the case, because we thought that at that time there hadn't been long enough for quasars to sort of collide together in the way that they're seen to be doing in this particular instance. I might just read, this is a press release from Noir Lab, the National Optical and Infrared laboratory in the United States. It's the NSF's optical and infrared observatories. Their press release on this, which, by the way, if you want to check it out, it's called Dual Quasars Blaze Bright at the Center of Merging Galaxies. Lovely headline. It starts.
Well, they're not talking about the two of us then.
Well, that there could be a metaphor in there for you and me. I'm sure we'll blaze bright as long as people listen to us.
Yeah, probably more like the burnt out husks of quasars. We are.
Yeah, they are correct though in that you've got to go back a long way in time to see us, because neither of us belong in the 2020s. Well, maybe we do.
Well, we're here. We just didn't have a choice.
The word fossils comes to mind, but I don't know why. Their press release starts off: astronomers using an array of ground and space-based telescopes, including Gemini North on Hawaii, have uncovered a closely bound duo of energetic quasars, the hallmark of a pair of merging galaxies, seen when the universe was only 3 billion years old. This discovery sheds light on the evolution of galaxies at cosmic noon, a period in the history of the universe when galaxies underwent bursts of furious star formation. This merger also represents a system on the verge of becoming a giant elliptical galaxy. So quite a bit to unpack there. Cosmic noon is something that...
I like that term.
Yeah, I don't think we've mentioned it before, but it comes up a lot in, when I go to learned discussions about astronomy in conferences and seminars and things like that. Cosmic noon is one of the hot topics because it's that period, when the universe was just a few billion years old, when star formation was at its peak. So the formation of stars since that cosmic noon has been falling away. It's still going on, but it's not anywhere near as energetic as it was. And quite interestingly, the birth of our own sun is considerably later than that. So our sun was formed in the cosmic afternoon.
Right.
For about 4.57 billion years ago.
That's because it slept in. Or had a big night or something.
Had a big night. Well, it may be that it waited around until the interstellar medium was rich enough with elements that were forged in previous generations of stars that gave it enough of the raw material of planets to actually form a solar system. So that sleeping in might have been quite intentional.
Yeah, well, it worked out for us.
Yeah, it did work out for us, that's right. But the other thing that statement says, the merger also represents a system on the verge of becoming a giant elliptical galaxy. Giant elliptical galaxies are the other kind of galaxy. We all tend to think of spiral galaxies, but almost as numerous are galaxies which are the shape of a football, basically, but don't have spiral arms. They don't have clouds of gas in them that are forming stars, because we think the star formation has completely ended. Run out of gas, literally, within the confines. So, as he said, this merger is basically two galaxies whose star formation is taking place violently, and there's this energetic stuff going on in the center with a supermassive black hole. But very soon, this thing will calm down and it will become one of these elliptical galaxies. It's what will happen, by the way, Andrew, to the Andromeda and Milky Way galaxies in 4 or 5 billion years when they collide to become a single object, which has been called Milkomeda, as you have discussed before.
Yes. Dear. Have quasars short-lived?
Yes, they are, which is probably why, we don't find them today. I mean, they're short-lived on timescales much, much longer than human timescales are, but they will eventually run out of gas. And, we see that when you look at the distribution of quasars as you look back in time. Yes, they're very active 4 or 5 billion years ago. They're everywhere. But then they start dwindling off to nothing as you get to our present epoch in the universe. And so that tells you that they don't last forever. One of the interesting things about them is that they do vary in brightness. I think I alluded to that a minute ago, which is thought to be due to, just how much stuff is falling into the black hole or falling into the black hole's accretion disk at any one time. So that is a useful facet, because by observing the way the brightness of a quasar varies, you can learn a lot about it. In particular, it's what told astronomers that quasars were very mysterious objects when they first started looking at them in the 1970s and 80s. Because if you've got something that varies on a timescale of maybe a day, what that's telling you is that it's smaller than a light day across, because otherwise the light coming from the back of the object will blur out the light from the front. So variations like that give you an upper limit on its size. And a light day is a very small amount of space for the amount of energy that was coming out from them. They were thought to be unbelievable at first, and it was eventually black holes that were realized as the culprits for how quasars work.
Have we actually ever seen one? Probably, obviously we can't see them directly, but we can use measurements to detect what they are. Have we seen one fizz out?
No, I don't think that's ever been seen.
Mm.
You see the variations in brightness, but the fizz-out process might take, 10 million years or something like that. So,
I can wait.
yeah. Well, we've waited this far, haven't we? So we might as well keep on.
Yeah. But quite a surprise, I suppose, is the fact that these date back so far. That's the really interesting part of the story, that they've been around a lot longer than we would have anticipated, I guess. Mm.
That's right. One caveat here: if anybody does have a look at that dual quasars blaze bright press release from Noir Lab, there is a lovely illustration of it, of these two quasars. But it is an artist's impression, because we simply don't have the telescopic magnification to see galaxies 10 billion light years away in that detail. It's an artist's impression of what it would look like if you were close up to it.
They're very good artists, though, aren't they?
Fantastic. Yeah, it looks perfectly like a photograph.
It does.
A bit of a worry, because, confusing artist's impressions and photographs, or digital images, I should say, is it's a risk that you take when you put things like that out there.
Yeah, I suppose artificial intelligence is now going to complicate that even more.
Yeah.
Some of the things they've come up with through AI recently have been quite extraordinary.
Indeed, it'll make it look even more like real images.
Yeah, yes, indeed, absolutely. All right, if you do want to look at that story, you can go to the noirlab.edu website. That's noirlab.edu.
Okay, we checked all 4 systems and skiing with a go.
Space Nuts.
Okay, Fred, let's move on to our next story, which is this mystery hotspot or band or whatever you want to call it on Saturn. Now, they think they might have figured this one out.
Yeah, that's correct. It is something that I wrongly alluded to as a recent discovery. This hot band, which sounds very musical, doesn't it?
It does. Yeah,
a really hot band. Anyway, in Saturn's northern hemisphere, because it goes back, the discovery observations go back to the 1970s. What is it? Okay, it is a bar of light. By that I mean something that is in a straight line, but quite broad, not a narrow line. But it goes all the way around the planet Saturn in its mid-northern latitudes. So it is a bar of light, but it's particularly special light because it is something called Lyman alpha light. And what that is the light in the ultraviolet part of the spectrum, which is emitted by excited hydrogen. So that hydrogen that is in that region of Saturn's atmosphere is in a state of excitement, which causes it to emit this ultraviolet light with a particular wavelength. It's well in the ultraviolet, so you need to be above the atmosphere to be able to detect that. So
with a lot of sunscreen on.
Exactly, that's right. Highly energetic radiation. So the mystery has been why it's there, and it goes back to, or the solution goes back to something that you and I spoke about, I think about 2 or 3 years ago. I know because I wrote about it in Cosmic Chronicles, which I meant to say the other day is called Exploding Stars and Invisible Planets in the United States, rather than Cosmic Chronicles. There's a chapter on Saturn in there.
Which reminds me, Fred, we've got a new episode, a new segment that we're introducing into the show, and it's called "How Many Weeks in a Row Can Fred Flog His Book?"
Yeah, okay. Look, there's probably a competition here, because we could have something like that just by substituting Andrew for Fred. Although I have to say, you have been very quiet about your excellent books in the last few weeks.
I'm still working on the audio edition of Parallax. I'm more than halfway through it. It's a slog trying to record audio books. It's a very long slog.
Yeah, I bet it is. I can imagine.
And it's my biggest book in terms of length, and so it's going to probably turn into a 10-hour audio book when it's finished.
Wow. So
Yeah,
this must have more than 100 words in it, this book.
it definitely does. Yes,
Quite a big
yes,
one. Yeah.
yes.
Yeah, sorry. The reason why I mention books is because it lets me date things when we've talked about them.
Yeah,
Because I remember, what goes into a book is something usually that you and I have talked about. And what we talked about, as noted in Exploding Stars and Invisible Planets, how many mentions that? 4. It was the rain of material falling on the surface of Saturn's atmosphere from its rings. This phenomenon called ring rain, which I do remember writing about this, and that there's two different sorts. There's just stuff that drops down from the rings onto Saturn's equator because the rings are aligned with the equator. But there's other stuff that gets transported, I think, if I remember rightly, by magnetic interactions to the middle latitudes of Saturn. So again, it's ice falling from the rings, which are essentially falling to pieces. That's the bottom line. The rings are from the inside are actually cascading downwards into Saturn's atmosphere, which implies, of course, that they're temporary. And in fact, they're thought to be very temporary on the timescale of maybe 100 million years or something like that. So you've got this ring rain that's sort of focused down onto the mid-latitudes of Saturn, as well as stuff dropping straight down towards the equator. I do remember, going back in time again, the old memory kicks in here. Of course, when when Cassini, the spacecraft that was in orbit around Saturn, when that flew between the rings and the planet's surface, it actually basically got rained on. It collected some of the molecules that were falling from the rings as it passed through that ring rain. So it was able to measure what they are. There's water in it. There was other stuff as well, carbon monoxide, I think. Anyway, that's all background. The bottom line is that this story now identifies the ring rain that's going to Mars's mid-latitudes as being the reason why this Lyman alpha bar exists, this highly visible ultraviolet strip around the northern latitudes of Saturn. And there is clearly some interesting chemistry going on there. When the ring rain hits the atmosphere, and Saturn's atmosphere has got a fairly high proportion of hydrogen in it as well, that there's some interaction here that causes it to glow in the ultraviolet. I'm not sure whether the scientists who are working on this, some of whom come from France, actually, the Institute of Astrophysics in Paris, whether they have absolutely identified the mechanism by which the Lyman alpha takes place, but they've certainly pinned it down as to being the source of why that Lyman alpha radiation is there.
Yeah, it's a fantastic composite image they've created too on the Science Alert website. It in the ultraviolet spectrum, it looks fantastic. It looks like a big, beautiful blue beach ball.
It does, doesn't it? Slightly flattened because Saturn is the most oblate object, or the most oblate planet in the solar system. By that I mean it's the most squashed at its poles.
Yeah,
it's a lovely image. And you can see the rings as well.
Yes, you can. And you say that this has been caused by the ring rain. Does that tell us what the fate of the rings is going to be in time if they're raining down onto the surface of Saturn?
Yep. Tells us that they are dribbling away, bottom outwards, with that 100 million year or thereabouts timescale that I mentioned a few minutes ago. That's what's likely to do it. The rings will probably end up looking more like the rings of Jupiter, Uranus or Neptune, which are very, very thin and pretty anemic looking compared with Saturn's rings.
Yeah. So we're kind of lucky to be in a time frame where we can see so does that also suggest that the rings around the other gas giants were much more significant in the past?
Maybe so. That's right. And I think the converse argument, and I think the headline that I remember you latched onto very well, was that the rings of Saturn might not have been there when the dinosaurs were alive. because they're thought to have only been, created within the last 100 million years or so. You can't tell any more accurately than that. And of course, the dinosaurs were here until 66 million years ago. So it's it is. It's we are fortunate to be living on our planet at the time when we have this pearl of the solar system in our skies, one that anybody can look through a small telescope and say, "Wow,
I've done it."
Yes.
My telescope's right there. And I took your advice and got myself a 90-degree eyepiece because one of the frustrating things about it is crunching down at my age to try and look into a 45-degree angle eyepiece, and it's a nightmare. But I've got the 90-degree now, so that makes it a lot easier. Not that I've had much time lately, but I'm going to get back out there and do some observing. I'm still hoping to see the aurorae that have been prominent in the skies in recent times, because they've been seen as far north as here.
Yes,
and some beautiful images being published about those, but that's completely beside the point. I was just talking about telescopes, but Saturn, is a spectacular thing to look at live through a scope. And Jupiter too, if you can get it at the right angle, you can almost see what's going on with that as well. You can see that it's very, very colourful, lots of different reds and oranges, and it comes through. It's beautiful to observe. Sometimes it's just a blink of light, and you can't really make much out at all.
Yeah, that's right. On a good night, particularly when the atmosphere is pretty stable, and you would get that out in Dubbo. More than we do here in Sydney, but to see the cloud bands on Jupiter, which you can with a small telescope. And of course, the other thing to look for with Jupiter is the 4 bright moons, which change from night to night.
Yeah, and they appear as bright dots sometimes and it looks, but they're in a line.
They're in a straight line.
Yeah, it's amazing. Yeah.
Great stuff.
Yeah, I've had the grandchildren outside a couple of times to look at the moon, and they're so young and absorbing so much information, but you put the eye on the eyepiece and you've got the moon focused, and they just go, wow, because it's so different looking at the moon through a telescope, and it's an extraordinary thing to just, I'm mesmerized by it. I've taken so many photos of the moon through the telescope and with a digital camera, but it's an amazing object. I think we got away from the point, but the hot spot on Saturn is self-inflicted by ring rain.
By ring rain, that's right.
Yeah. So basically Saturn's dumping on itself. That's what's happening.
Yep. It's, it's a catastrophic ending taking place in slow motion for the rings.
Yeah, so it will ultimately have maybe just a remnant thin ring.
Yeah, maybe so.
And that'll be that. Or could it just all disappear completely?
I guess so. There may be, I don't know, there might be a stable region where it's... Because the rings are highly resonant with some of the moons of Saturn. And some of the moons actually are kind of shepherded within the rings. It's all by gravity. It's marvelous stuff. I mean, Cassini was such an amazing mission. What we learned about the planet.
Yes, indeed. Yeah, and we'll watch, because I think those rings will be gone in a couple of weeks. But if you want to chase that story up, you can go to the Science Alert website. But they've also published their findings in the Planetary Science Journal. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Now, Fred, it is time to say goodbye after we have answered some questions. And we will cut straight to the chase. This is Ken, who is asking about the Square Kilometre Array. Eventually.
Hi, Fred and Andrew. Ken from Queensland.
Queensland, sorry.
Fan and Patreon supporter. I've got 2 questions about the SKA. Firstly, most people know about the actual scopes themselves in Australia and Africa, But could you tell us more about the back end, where all the data is going to be processed and how? And secondly, with the SKA, considering the enormous power it must be using, is it going to be carbon neutral? Thanks for your help.
Thank you, Ken. Sorry, I thought you were in WA, but that's where the SKA is. You're in Queensland. Hope all is well. And thank you for being a patron. That is wonderful. Thank you so much. Where will the data be processed?
Yeah, that's a great question. And of course, it's one of the critical things. When the SKA was first mooted more than 10 years ago, in fact, it's probably more like 20 years ago now, it was known then that there was not anywhere near enough computing power on Earth to deal with what would be coming from this telescope. And so the computational requirements for it have evolved since it was planned. Some of the data, it's a complex thing. The data are actually transmitted around the site on fibers, optical fibers, and then they go to kind of individual processing centers. I'm thinking now particularly of SKA low. That's the low frequency arm of the Square Kilometre Array, which is what will be in Western Australia.
Yeah,
at the Murchison Radio Astronomy site, which is now known as Inyarimana Ilgari Bundara, which means sharing sky and stars in the Wodjiri language. Lovely stuff, fabulous. So that site, it has some of the sort of pre-processing computer power actually within the arrays themselves. Remember, you've got arrays of dozens of Christmas trees, metal Christmas trees, which are spread over eventually something like 75 kilometres.
Yeah.
But then they go to central sort of processing units, which are called correlators. But then they go from there to, I think there's a data centre in Geraldton, which is the nearest large town. It's on the coast, 350 kilometres away, and eventually down to Perth. And the major data processing centre there is the Pawsey Computer Centre, which is in Perth. I've visited it a couple of times. It's a great place with some extremely impressive machinery in it. But the other point is that the member countries of the SKA will also have what are called regional data centers or regional data centers, which will have their own capabilities for doing this. So you can't send all the raw data from the telescope to these things because there's just too much of it. So it's got to be sort of reduced at some level. And then it goes to the regional data centers as well as the Pawsey Centre. And that means that you can distribute it to the actual users of the telescope who are in the participating nations.
Yeah.
Sorry, go
on.
No, you go.
I was just going to say, I'm looking at some of the photographs from the work, and the Murchison facility looks kind of like a metal pine forest.
It does. Yes, that's right.
It's a very weird look, but they just look like lots and lots of pine trees made of metal.
There are going to be 131,000 of those pine trees, and at Christmas time, every one of them has to have decorations on them.
Yes, and a bauble on top. Yeah.
The other part of Ken's question is a good one. Will it be carbon neutral? Not quite, but that is the ultimate aim, I think. There is a large solar array at the observatory at Murchison, which I think at the moment provides about a third of their power. I think that's correct.
Well, that's pretty good.
And I think the rest is diesel. So I might be wrong there. I'm just kind of remembering things that I've heard. I've been interacting with SKA people, but the aim is, yes, to make it carbon neutral. I mean, if you can't use solar panels in WA in the Western Desert there, you don't have much chance. Although I have to say, the day that I visited that observatory site back in 2018, it absolutely poured down. It was,
Well, wash the rust off.
certainly washed the rust off me, I can tell you.
Yeah, yeah. It's an extraordinary facility. And when's the the commissioning date? When's it?
Ultimately, it's the late 2020s,
Yeah.
2027, 28. It's one of these things that you can actually kick things off before it's finished because it's an array. Just let me mention, I may have mentioned this when we spoke last week, Andrew, but there is a virtual reality movie called Beyond the Milky Way, which effectively takes you to the observatory site and it does it in 3 dimensions with all the details of what it's like there. It's a lovely movie. At the moment, it's showing in Canberra, but I'm sure it will find its way to where Ken is up in Queensland. It's one not to be missed, and have a look at if you get the opportunity.
Yes, indeed. Thank you, Ken, for your question. Let's now go OS. We're heading to bear country. I'm pretty sure. I'm sure he said. I had to listen twice, but I'm sure he said his name was Bear.
Hello, this is Bear Hands from Perth, Western Australia. Now, I was taught that light comes into the planet as visible light, hits the surface of the Earth, is absorbed and then reflected as a lower energy infrared, which is what causes the greenhouse effect. What happens to the infrared that is directly radiated from the sun? Does it hit the Earth and get reflected as a lower energy microwave? Also, if you stand in front of a fire, it's giving off visible and infrared light. Is it giving off other frequencies of light? And what is infrared's relationship with the thermal heating of particles from the fire? Does the fire's heat come from infrared or the oscillation of air particles, or both? Why do we feel infrared as heat? Is heat just how the human body senses infrared? What I'm asking is essentially, how does heat relate to infrared, and how does infrared relate to heat? I've wondered about this phenomenon since I was a very little boy.
Wow, that's really interesting. I don't think we've ever had a question like that before. We've talked about light a lot, and infrared light and ultraviolet light and, everything basically. But yeah, how do we feel infrared light, and how does it transmit? How does it do what it does? That's a really good question. I'm sorry you've been struggling with it for so long.
So the last bit is, it's more physiological than physical. The fact that infrared radiation, we can feel it by the fact that the radiation hits our hands or face or whatever.
Yeah.
And sitting in front of a fire, that's exactly what's happening. And the nerve endings in our skin are obviously sensitive to that and react to it in the same way as the retina of the eye is sensitive to the visible light and reacts to it. So there's a physiological process taking place there. But I wonder if the kind of broader answer to these questions is about the spectrum of light, because first of all, if you think of sunlight, the sun behaves a bit like something we call a black body, and a black body is, if you think of something like a lump of iron that's black, it gets different colours at different temperatures. So as you heat it up, it will be, it'll be red hot at temperatures in the region of 1,000 degrees, perhaps. You heat it up more, it becomes white hot. If you could heat it up even more, it would become blue.
Wow.
And what's happening is that a black body, like that lump of iron or whatever it is, and the sun behaves in a similar way. It emits a spectrum of light, which is like it's just a curve that starts off low in the short wavelength end, rises to a peak, and falls away again at the long wavelength end.
Yeah.
And it's where that peak occurs. The peak occurs in a different place depending on the temperature. So, for a human being at a temperature of 37, whatever it is, 37.5 or thereabouts Celsius,
yeah,
we, at the peak of our black body curve, which is what that thing is called, is in the infrared. It is actually heat. And you know that because if you could probably feel the heat from somebody's body without actually touching them because they're radiating infrared, and it's at a wavelength of about 10 microns, 10 millionths of a meter. That's correct, isn't it? Yes, micrometers, 10 microns. So 10 thousandths of a millimeter, as it was, as it is. I'm just thinking about this because that's ridiculous. Anyway, it's 10 micrometers is it's the correct answer.
Okay.
I always get because we use something called nanometers, which are billionths of a meter, to measure the wavelength of visible light. So 1 micron is very much in the infrared, but 10 microns is what we would call the far infrared. Anyway, that's how a human body operates. If you heat things up a bit more, the peak of that curve moves downwards in wavelength until eventually it creeps into the red end of the visible light spectrum, and that's when it's red hot. And if you heat it up even more to about 5,000 degrees, that's when it becomes white, because the peak of the radiation curve is right in the middle of the visible spectrum. So you've got all the spectrum there being emitted, and that, as you know, adds together to make white light. And if you heat it up even more, as you do in stars, it goes blue. So the sun is also a black body emitter. So not only does it emit white light, the peak of its radiation is actually in visible light, but there is a tail on either end where it's emitting ultraviolet light. We know that because that's what makes us sunburned. And it's also emitting infrared light as well. So the light from the sun is a mishmash of visible light, ultraviolet, and infrared. And it's all determined by this strange shape that I've just mentioned. So I don't know whether that helps. It means that infrared radiation, of course, is falling on the Earth because that's how we feel the warmth of the sun. It's the direct radiated heat of the sun. In a fire, it's the same thing. If you're sitting in front of a fire and not touching it or not near it, the heat that you feel is infrared radiation. But the convection, the stuff that's being heated up and making the smoke blow away, that is the convection is the other process, or one of the other processes by which heat is transmitted. Convection's exactly as we were just saying, is the movement of air molecules. The third way of heat being conducted is actually conduction, where you're physically touching something and
warming it up,
coming through it. I don't know whether that answers the questions, but
probably touched on one or two of his 50 questions.
That's more or less what we did. But the bottom line is, I've lost my pen here. Let me just go.
Here, I've got one.
Oh, thanks, Andrew. Oh, yeah. I've got a blue one. You've got a red one.
It's black.
Oh, okay. It's black. That's white.
It's a black
white
pen.
In a red. Yes. Anyway. The pen is probably a black body, so that if you heated it up, it's the right temperature, it would emit the right wavelength. So yes, it means that the sun is radiating infrared. As far as I know, that energy is not converted into microwaves by the surface of the Earth, which I think was another of the questions. But never mind that. It's the radiation, the heat radiation that we receive directly from the sun actually just goes into warming up the surface. And so that's still emitting in the infrared, but at much lower wavelengths than microwaves.
Okay. Hopefully, Bear, that got you covered. But if we missed anything, you're more than welcome to send us a follow-up question. And thanks for getting in touch. Nice to hear from you. Now, I've got one more quick one. This one comes from Richard, who's on the sunny coast, I assume Queensland. Now, he says, good morning, Andrew and Professor Fred. I'm thinking about the possibility of life on Enceladus and other ice moons. Just a question about pressure in the oceans of these moons and possibly of life. Pressure in our oceans increases by about 1 atm every 10 metres. Mariana Trench is 11 kilometres deep and the pressure at the bottom is 1100 atm. Yet even down there, life prevails. Enceladus and Europa are thought to have oceans much, much deeper than Earth, approximately 40 kilometres and 6 to 150 deep, respectively, but are tiny compared to Earth, and so gravity is much less. What sort of pressure is thought to exist in these oceans from just under the ice down to the bottom? Do you think this pressure would present a problem for life as we do or don't know it? Given that this doesn't seem to be an impediment here. And thanks for the great podcast. Thanks, Richard. Nice question. Love it. Love it.
Me too. And I agree with Richard. So everything he says is correct, that, the oceans are much deeper than ours, but these are tiny objects with much lower gravity. So the number of atmospheres of pressure that you've got, that's the ATM bit, is much lower. It is probably it's not lower. It's probably comparable with. I'd need to look up these pressures, which we'll be able to do offline, and I will have a look, because they're probably well estimated by knowing what the gravitational pull of Enceladus, for example, is, how much water's there. The other thing that pressurizes the water is the layer of ice on top. Because
I suppose so.
That is seriously thick, and maybe 25 kilometers of ice on top of a liquid ocean. That might be one of the reasons why it's kept liquid, although there's probably internal heat as well from Enceladus. The last time I looked, the heat budget of Enceladus needed to keep the ocean liquid hadn't, I don't think, been completely accounted for. I think there's still mysteries there. But yeah, the bottom line is that I think Richard's right. If living organisms can exist at the bottom of some of these trenches on the oceans of the Earth, which they do, then there's no reason why they shouldn't in some of the depths of the oceans of Enceladus, Europa, and some of the other water worlds that we know are out there.
Which reminds me, the other day, some Australian scientists, along with some of their Japanese colleagues, achieved the deepest fish catch in human history at over 27,000 feet. And they caught a snailfish.
Yeah,
Ugly damn thing. Ugly as.
Yeah, but, if nobody can see you,
you don't need to look
good. To be beautiful.
Yes. Well, unfortunately, the internet fixed that for you and me. But anyway, that's the way it goes. But yeah, I suppose the other thing is that if life has found a way on those particular moons, Europa, Enceladus, and maybe a couple of others, it would adapt to whatever the circumstances are. So it probably wouldn't matter to the life what the conditions are, because that's what they've adapted to, just like we have on Earth.
Yeah, that's right. In fact, it's more than adaptation. There'd have to be that environment would have to be a benign one for whatever life was kicking off there. So your starting conditions are such as that if you're going to get life, it must be able to survive at those depths.
Yes, and I suppose one day we'll figure it out when we go and have a look.
We might even find out one day, which would be very exciting.
What's the next mission? Is it Europa Clipper? Is that one?
Yeah, that's right. Yes. No, it's Juice. Juice is going before Europa.
Juice, that's right. I knew that. I talked about that the other day. Okay, Richard. Hopefully we helped. And yes, we don't know, but it's very possible there's life there, and it's adapted. If the original recipe was there to get life kicked off, I guess that's the way to put it. Thanks for your question. Thanks to everybody who sent questions in. And a reminder that if you do have a question for us, jump on our website, spacenutspodcast.com or spacenuts.io. The AMA link at the top will take you to a text-based interface, or you can send us an audio question if you've got a device with a microphone, or just the tab on the right-hand side of the homepage, which will enable you to send audio questions. Don't forget to tell us who you are and where you're from, and have a look around while you're there at all the wonderful links and bits and pieces and Fred's books on our website.
I gave Fred and Andrew's books as well.
Are they there? I've never looked. Dear, oh dear. Fred, we're done. Thank you so much.
Great pleasure. Always good. Speak on the next episode of Space Nuts.
We will. That's Fred Watson, astronomer at large. And to Hugh in the studio, he couldn't turn up today because he's decided to have much more fun than being with us by having an eye injection. Ooh, yow, nasty. That's macular degeneration for you. And from me, Andrew Dunkley, thanks again for listening or watching, and we'll catch you on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.